We're going to switch gears now, and we're going to focus on defining the derivative. And really, this section should be labeled defining the derivative at a point, because that's really what we're doing. We're defining the derivative at a particular point. So at one point in particular. So this is different than defining the derivative in general over the interval. So we're defining it at a point. This is the second major construct in calculus. The limit is still the most powerful, but the limit is super difficult and time consuming to get it through. And so we came up with the derivative, which is a faster way of doing a lot of what the limit allows us to do. Now, the relationship between the derivative and the integral, the third major construct, was created by both Isaac Newton and Gottfried Leibniz. Newton got there first, but Leibniz published first. And we'll be very grateful that Leibniz did publish, because his notation is pure genius and we're still using it some 330 years later. Newton's notation was sort of a nightmare, not really a good one at all. It was really a bad notation, and we do not use his notation anymore. The only college I know of that regularly uses his notation is MIT, and they just like to be different. All right, that's just MIT. All right. Okay, so we're going to take a look now at the tangent lines and secant lines again. We're going to be talking about the relationship between the tangent line and the secant line. So we want to remind ourselves that the secant line is the line that cuts through the graph at 2 points. The tangent line barely touches the graph. It just barely skims along and then comes off again at one single point, close to the point that we're looking at. So we also want to talk about what is a rate of change. The rate of change is the rate at which one variable changes with respect to another, which is just another way of saying slope of the secant line and slope of the tangent line. So the secant line, of course, is this one right here, where it's cutting through the graph at 2 places. And we can do f of x minus f of a over x minus a. And that's one way of writing down the slope of the secant line. You have 2 different points, a f of a and x f of x. And this is the difference in the y values over the difference in the x values. So really, this is y1 minus y2 over x1 minus x2. It's the same slope formula that you've been using at this point for years, right? I mean, you've been doing this for years. So there are a couple of applets here. I kind of like the second applet, I think, is the one that I prefer. So we're going to kind of look at this. So there are 2 of them, unless I move them around, because I like the second one better. Let's see what the first one looks like. Actually, I think I must have moved them around. All right, so this one gives you the ability to do what's called the difference quotient, which is what we're looking at today. We're going to be studying the difference quotient. And we're not going to look at the symmetric difference quotient, so don't click on that one. We will be looking at the derivative eventually. We'll look at delta x and all the different ones, and then we're going to be looking at f prime later on. So what we're talking about over here in the graph is you've got a change in x, which is called delta x, and a change in the y value, which is delta y. And this gives you the rate of change of the function, how the y is changing with respect to how the x is changing. And of course, if you change where your a value is, or you change where your h value is, then you're going to get some difference. Now, h is how close the 2 points are to each other, all right? So this is a different way of writing down the same formula. Instead of writing f of x and f of a, they write f of a and f of a plus h, as in h is a little bit moved over. So a and h are not the same location. So on our graph right here, they would call this a plus h, f of a plus h. So what is a? A is this spot right here, and x is equal to a plus h, where this distance in between them, that's your h, All right, that's the little bit that you've moved over there. Okay. And the nice thing about this over here is it's giving you the value of the difference quotient right here. It's calculating it for you so you can check your values, be sure that you're doing it right. You're allowed to change the function, so you can use this on your homework if you want to change the function value and see whether or not you're calculating it correctly. The other applet does the same thing, but a little bit simpler. It's a simpler setup. It does less. It does give you the ability to change the function, to set the value of A, and to change the value of H a little bit. It doesn't allow you to change H a lot. It only goes up to 1, and then it can get smaller and smaller and smaller. Do you see how the secant line, the point is getting closer and closer to A as I make H smaller and smaller? They're getting closer and closer together over here on the graph. Now the question is, as H gets smaller and smaller, it approaches the graph of the tangent line, which is of course graphed here in, I think, blue, all right? Or green, it's hard to tell. So let me move H out a little bit so I can tell. In black. So the tangent line is in black. The secant line is in blue. And as I change the value of H and it gets smaller and smaller, notice how the secant line is getting closer and closer to the tangent line. Do you see how close they're getting? As H goes to 0, the secant line approaches the tangent line. And that's really what we're looking at here, is how the secant line approaches the tangent line. All right. And there's the tangent line on this one. And we can allow H to get smaller and smaller. And notice how the secant line, again, is approaching the tangent line. I'll get my screen back up. So you've got this sort of pinkish violet line that's getting closer to the red line. As H gets smaller, the secant line approaches the tangent line. And that's basically the idea of the derivative. And that's where we're headed, is what is the derivative, right? Bless you, Brittany. Okay, so now we've got tangent and secant, and we want to find the slope of the secant line between the values of x1 and x2 for the function. This is just straightforward right out of middle school or high school, where you're doing the y2 minus y1 over x2 minus x1. This is the slope of the secant line that cuts through the graph. So this is going to give us f of x2, we'll do x2 first just for fun, minus f of x1 over x2 minus x1. So that's going to be f of 3 minus f of -1 over 3 minus a -1. The things to watch out for are the double negatives. The formula has a subtraction in both the numerator and denominator. If the number is negative, it's a double negative, right? So f of 3 is going to be 8 times 3 is 24, minus 3 is 21. F of -1 would be -8 minus 3 is -11. Notice that gives us a double negative in the numerator, and we already had the double negative in the denominator, okay? It does help if you will make the negative where it belongs, all right? A subtraction sign and a negative sign are not actually the same sign. The subtraction is shorter and below, and the negative is slightly longer and above, all right, where the subtraction is. So we have double negatives, which become positives, and I'm getting 32 over 4, which reduces to 8, right? This is the rate of change of y with respect to x. In other words, it's the slope. Y is changing 8 units for every 1 unit that x changes, all right? So we have the slope there. Okay, let's repeat the process on the next function. So we're going to do the same thing. Slope of the secant line. Let's do f of 27 minus f of 1 over 27 minus 1. This is going to give me 6 times x which is 27 to the 2/3 power, plus 2 times 27 to the 1/3 power. This one I have to write out, minus, in parentheses, 6 times 1 to the 2/3 power, plus 2 times 1 to the 1/3 power, all divided by 27 minus 1. Now, what does the 2/3 power mean? 27 to the 2/3 is the cube root of 27 and then square it. So the cube root of 27 would give you a 3, and then 3 squared would give you 9, right? And the 27 to the 1/3 power would just be the cube root, which would be 3, all right? Now, 1 to any constant power is going to be 1. So that part works out pretty easily. So now we have, for the slope of the secant line in the numerator, we have a 6 times 9 plus 2 times 3 minus, in parentheses, 6 plus 2, which is, of course, 8, all divided by 26. This gives me 54. This gives me 6, and that's minus 8. So that would give me 52 divided by 26, which is a rate of change of 2. So our rate of change is 2 units in the vertical direction for every 1 unit in the horizontal direction. And I'm thinking of 2 as a fraction of 2 over 1. And here is a graph of the function that we've got right here. This is a graph of that and the slope of the secant line. Let me see if I can get the secant line on here. There's the secant line right there. All right. So what we found was the slope of that line. All right. And that is the rate of change for the function, the average rate of change. All right. As x gets closer and closer to a, the slope of that secant line starts to approach the slope of the tangent line. Now, we saw how in the one applet, instead of using f of x and f of a, they wrote it as f of a and f of a plus h, so that we can write the expression in this form right here. So remember that a and x are really just a, and a moved over a little bit to a new location, a plus h. It's really the same thing. So instead of calling it x, they're calling it a plus some small distance h that they've moved over. And then they rewrite the difference quotient as f of a plus h minus f of a over a plus h minus a. So this is the same expression that we've had before. And this is our change in the x variables. All right. But it turns out that a plus h minus a reduces to h. And this is the form of the difference quotient that you probably used when you studied Algebra 2. So this is called the difference quotient. And it's a very famous formula because it leads to the definition of the derivative when combined with the limit. So when we take the limit of the difference quotient as h gets smaller and smaller, we get the slope of the tangent line. So let's look at this graph again, and we're going to take a look at it again. A is fixed, and I'm going to change the value of a. Remember that this red line that's up here is the tangent line, and I want you to watch what happens to that sort of pink violet line. As h gets smaller and smaller, that violet line starts to approach and come close to the tangent line. So as h gets smaller, now it's 0.28, now it's 0.12, now it's practically 0. Does everybody see that? Once it's 0, the secant line is the tangent line. So as h goes to 0, the secant line becomes that tangent line. So this is what we're talking about, but this is a limit, all right, because thou shalt not divide by 0. We're not allowed to let h be 0. So what we do instead is we take the limit of the difference quotient as h approaches 0. And that gives us the derivative as we get closer and closer. Let's take a look now at the tangent line on a particular graph over a series of tighter and tighter intervals. This is going to be like zooming in with an electron microscope, okay? We're talking about zooming in super, super, super close. So we're looking at the square root function, which basically is like the upper arm of someone doing the American crawl, right? You know, where they come like this. So this motion right here, that's pretty much what the square root function does. Starts at the origin, arcs up, and then it continues to increase, but not at a very rapid pace, all right? And what they're doing is we're going to take a bird's eye view, and we're going to focus on the point where x equal 1, all right? So we're focused on this little square right here, where x is 1 and y is 1. So we're looking at the point 1, 1, and we're going to zoom in on it. So in the second picture over here, you can tell they've zoomed in from looking at the scale at the bottom. And the 0.11 is right here again. And notice that over that small interval, it's hard to detect the difference between the tangent line and the curve. So we're talking about this spot right here, which is 1, 1. At that spot, 1, 1, the tangent line and the curve almost look like the same curve. And then they zoom in again, get even closer. When you're looking down here at the next one, we're going to come in even closer. Down here at the bottom, 1, 1 is going to be this point right here. This is that same point, 1, 1. And you can tell that it's almost indistinguishable, the tangent line from the actual curve. In other words, if you're very close to 1, the tangent line is a super good approximation for the curve, isn't it? I mean, it's a really good approximation, and it's a line. So everywhere from about, 0.95 up to about 1.05, you can hardly tell the difference between the tangent line and the curve. And notice that they're both linear. Now let's compare this to the graph of the square absolute value of x. So we did square root of x. Now let's look at the absolute value of x. And I've circled the spot I want you to focus on, which is here at the origin 0, 0. So I want you to be focused at this point, 0, 0. And notice that the scale right now is -2 to 2. And we've got a corner here. So there's no tangent line because it's a corner. How are you going to balance a tangent line on a corner? You can't, right? There's no unique tangent line. And over here, we zoom in. You can see it goes from -0.5 to 0.5. It's still pointed. There's no way to get a tangent line on that point. Zoom in again between -0.1 and 0.1. Zoom in again between -0.001 and 0.001. It's still pointed. It doesn't matter how close you go. That part of the graph is never going to be linear. It's always going to be a corner. You cannot balance a corner on, or balance a line on a corner. It's like trying to balance a yardstick on a corner. It won't happen. All right. So that's the reason why there is no limit there at that point. The limit will not exist because it's a sharp corner. There's no unique tangent line at that point. So that's one of the first things that we learn. There are no derivatives at corners. You cannot balance a tangent line on a corner. So there are no derivatives at corners. The limit does not exist. Here's the definition for the limit, written in a couple of different forms. All right. There's another way of writing this one right here, which is probably, I would say, the one that I use more often than using the A form. I write x plus h minus f of x all over h. All right. So that's another way of writing it. This is the slope of the tangent line, not the slope of the secant line. When you take the limit as x approaches a of the difference quotient, or as h goes to 0, as they get closer and closer together, then the secant line becomes the tangent line. So you're getting the slope of that tangent line. And that's what we're talking about. Okay. So we have the slope of the tangent line and this formula, limit as x approaches a of f of x minus f of a over x minus a, where a is a fixed point and x is getting closer to it. And this one we're calling a plus h. We're calling x a plus h. And then the difference between the values is h. And as h gets smaller and smaller, the tangent line is what results from the secant line. Now, I expect you to have these memorized. This is something that I will ask on the exam next week. I'll ask you for the major forms. There is one more major form, and I will ask you for these. And that would be this one. This is the one that's used typically in physics. Instead of doing h, they use a delta x instead of h, because that's really what it represents. H is a change, a small change in the x value. So I will expect you to be able to write one of these down. And again, you can write this one in the A form as well. So this is also written sometimes as delta x goes to 0 of f of a plus delta x minus f of x over delta x. So I will expect you to write one of these two, and this one. So this is the first one. One of these two is the second one with h, and this is the third one with delta x. All right. So I will ask you, what are the three forms for the definition of the derivative? You will give me those three equations, and then I'll say, what is our hand-waving definition of the derivative? And the hand-waving definition of the derivative is the slope of the tangent line. And then I will ask you to apply one of those formulas to a particular problem. So we're going to practice that now, right? Now, what we're practicing in this first section is finding the derivative at a single point. So at one point and one point only. So a is fixed. So what we're talking about in 3.1 is a is fixed. A is known. A is 3. And we want to know, what is the slope of the tangent line at a equal 3, because we know what a is. So down here in example 3, it says use the first definition, which is given, to find the slope of the line tangent to the graph of the square root of x at x equal 4. At x equal 4, this is your a. So a is equal to 4. So what we're being asked to find is the slope of the tangent line, which is the limit as x gets close to 4 of f of x minus f of 4 over x minus 4. That's what we're being asked to find. The slope of the tangent line at a particular point, not just anywhere, but in a particular place. Okay. So what we're going to do is we're going to substitute in the function. So we have the limit as x goes to 4. F of x is the square root of x. And f of 4 would be minus the square root of 4, all divided by x minus 4. Now we can simplify the numerator because we know the square root of 4 is going to give us a 2. So we have the square root of x minus 2 over x minus 4. Now, if I tried to plug in, which should always be my first instinct, if I plug in, I get 0 over 0, which is one of those indeterminate forms, which tells me that that method didn't work. So I've got to back up and try something different. So what I'm going to try now is something slightly different. So I've got a square root, and I've got square root of x minus 2 over x minus 4. What technique would you try to get rid of that hidden factor that's causing 0 over 0? What would you try?
Multiply by the conjugate of the radical.
Yes, multiply by the conjugate of the part that's the radical. So the conjugate would be square root of x plus 2. So I'm going to multiply by that divided by itself because that's just the number 1. And this is going to give me the limit as x approaches 4 of x minus 4 in the numerator. Remember, when you FOIL the difference of two squares pattern, you get the first one squared, which gives me x. The outside and inside are identical, but with opposite signs, so they cancel. And then you get minus the last one squared. Now the denominator, I'm going to leave factored because I'm hoping that one of the factors will become the thing that is causing the 0 over 0. And there it is. All right, we can see it already. It's this x minus 4 over x minus 4. So we can see the factor that was hidden at first that was causing the 0 over 0 result. So now we can cancel that hidden factor. It does not magically jump to the numerator. It stays in the denominator. And now we have the limit as x approaches 4 of 1 over the square root of x plus 2. And then we try to plug in again. And we get 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, or 1/4. And that's our final answer. That's the slope of the tangent line on that graph when x is equal to 4. So when we're looking at one of our particular ones up here, I could make this x to the 0.5, which is one way to do, there it is. And a is, what do we say, 4? All right, so there's a equal 4. And we want to know what's the slope of the tangent line as it comes in and gets closer and closer. So as we get very, very close, we can see that it's getting closer and closer and closer. And we can tell what the value of it is coming out to be. If we want to see the derivative, we put the derivative over here. Notice I clicked on the third one down, which is derivative. It gives us the slope of the tangent line in the f of a plus h minus f of a form. And it's giving us 0.25, which is 1/4, which is what we got. And you notice over here that as h gets smaller and smaller, that value that they got for the difference quotient is approaching 0.25. Right? That's our rate of change, the average rate of change, or the rate of, that's the instantaneous rate of change at 4, right? At that particular price. Now, that's the formula that we use the most often, this f of x minus f of a over x minus a. That's the form we use most often when we want the derivative at a particular point. We know a is 4, all right? The other two tend to be ones that we use when we want a formula for the value of the derivative at any value of x, not just at 4, but at any value. But we can use any of them to find the value at a particular point, all right? The notation for derivative is the prime notation. And you'll see it looks like a single apostrophe. It is slightly slanted because it's italicized. So we have f, and we read this as prime. F prime of a is the slope of the tangent line, which gives us these three forms right here. You could give me these three forms right here on the exam, and that would give you full points for that part of the exam, right? I'm looking for the three. One with f of x and f of a, where x approaches a, one with h, where h approaches 0, one with delta x, where delta x approaches 0. I will ask them, you do have to memorize them. Okay, let's try another one. This one we're going to use the second formula, the h formula, which is the one that mathematicians use the more often. and we're looking for f prime at 1. All right, so f prime at 1 equals something. That means that a is equal to 1. So we're going to take the slope of the tangent line, and we have the limit as h goes to 0 of f of a plus h, but f of a plus h is going to be f of 1 plus h minus f of 1 all divided by h. We know what a is. A is 1. So we're trying to find the slope of the tangent line at a particular point, not in general, at a particular point, and the point is 1. So now we have to do what the function is. I better scroll back so I can see the function. I'm going to do this in pieces because I find that that works better for the difference quotient. So I'm going to find f of 1 plus h first. So I take 1 plus h and I replace the x in the function with 1 plus h. So this is going to give me h squared plus 2h plus 1 plus 3 plus 3h plus 2, which gives me h squared plus 5h or plus 6. Is that what you guys got? Okay, Shuri agrees. That's what she got. Now I want to find f of 1. So I'm going to repeat the process. So that's going to be 1 squared plus 3 times 1 plus 2, which is 1 plus 3 plus 2, which is 6. All right, so I'm doing it in pieces. I'm finding this piece first, and I'm finding this piece second, and now I'm ready to put them into the difference quotient. So I've got slope of the tangent line, limit as h goes to 0 of f of 1 plus h minus f of 1, all divided by h is equal to the limit as h approaches 0 of h squared plus 5h plus 6 minus 6, all divided by h. Notice that my 6's cancel. This is very common. If something doesn't cancel, you've probably made an error. All right, it's very, very common to get the cancellation. So if you don't get any cancellation, you better check your signs. So this is going to give me the limit as h approaches 0 of h squared plus 5h divided by h. You can factor the h out, or you can split it into 2 fractions, but it comes out of both terms in the denominator, not just one. Both terms are being divided by h, so you get h plus 5. And what would the limit be as h approaches 0? As h goes to 0, what would you get for the limit? Yep,
5.
Roz is right, and Jean is right. We get 5. All right. So what does that mean? That means that the slope of the tangent line at 1 is 5. So let's try x squared plus 3x plus 2. All right, so there's my graph, and I want to find it when a is 1. All right, and I think I need to probably scroll down a little bit so I can see it a little better, so I can see where I am on the graph, and you can tell that it is approaching 5. All right, the tangent line's approaching 5. You can take h, and as you make h smaller and smaller, notice that the values right down here in that purpley color, purple pink color, are coming down and getting smaller and smaller as h gets smaller and smaller, and they're approaching 5. And as we get smaller and smaller, they get closer and closer. All right, and the limiting value is 5. All right, And you played around with a limiting value sum in the previous section as well. So this concept is familiar to you, or should be. Okay. Let's take a look at this one. This is using the first formula again, but it's got a fraction in it. So we're going to have a complex fraction. It's going to make it a little harder. So we're looking at the derivative at 3. So we have f prime of 3. So a is equal to 3. So I'm going to go ahead and think of this as the limit as x approaches 3 of f of x minus f of 3 over x minus 3, which is going to give me the limit as x goes to 3. F of x is going to be 7 over x minus f of 3 would be 7 over 3, right? So I'm going to have a fraction there. And then the next thing I'm going to have in the denominator is going to be x minus 3. All right. Now, you have a complex fraction because you have a fraction in the numerator of a fraction. So the best thing to do is go ahead and write the entire thing as fractions in the numerator and denominator. So I'm going to put the x minus 3 over 1. Then I look at all the little denominators. So when we look at the little denominators, or the ones that are denominators inside the larger fraction, my little denominators turn out to be x, 3, and 1. So the lowest common denominator is going to be 3x. So then I'm going to multiply the numerator and the denominator by 3x over 1 over 3x over 1. I'm going to make it have the same complex fraction form as the original, and that will help me to get rid of the little denominators hidden inside. Remember to distribute, so you get this times that, that times that, and you get this multiplied by each term in the denominator as well. All right. So this is going to give me the limit as x goes to 3. The x's cancel for the first fraction, and so that gives me 3 times 7, which is 21, minus. And then when I distribute over the second fraction, the 3's will cancel, so I get 7x. And in the denominator, I need to go ahead and distribute this as well. So I get 3x times the x minus 3, but I'm going to leave the denominator factored. Right? Why would I leave it factored?
To see what cancels.
Yeah, to see what cancels. Hannah's correct. There might be something causing a 0 over 0, and in that case, I need it factored, so I'm just going to leave it factored. The numerator is not factored. That's where I had those complex fractions. So now I need to factor the numerator, and that's going to take out a 7 as the greatest common factor and leave me 3 minus x. Now I've got 3 minus x over 3x, x minus 3. These are very close, but they're opposite in sign. All right. 3 is positive here, negative here. X is negative here, positive here. So the way to deal with that is to factor out the negative 1. So make this a negative 1 times x minus 3. All right. If you do that, then you'll be able to cancel. So this is gone because we've replaced it with negative 1 times x minus 3. And now you can cancel the x minus 3's. And that's going to give us the limit as x goes to 3 of negative 7 over 3x. Now I should try plugging in. And when I plug in, I will get the value of negative 7 over 9, which is the value I'm looking for. Right? So the value of the slope of the tangent line at 3 is -7/9. Right? So we can look at this one over here. We can put this one in. We have 7/x. And we're approaching 3. All right. Oh, my bad. I put in 13. 3. There we go. All right. And so we end up with -7/9. All right, which is about -0.77777 and forever and ever. All right. It's a repeating fraction. And I know it has to have a pattern that repeats because it's the ratio of 2 integers. They always have a pattern. They either terminate or they repeat. Okay, let's try one more. Maybe 2 more, and then we'll look at velocity. So use the definition, the second definition, to find the slope of the line tangent to the graph of the x² plus x at a = 1. So what we're trying to find is the limit as h goes to 0 of f of 1 plus h again minus f of 1 all over h. So I'm going to come down here, since these are more complicated with their substitution factors, I'm going to come below, substitute it in first and get the values. So this gives me 1 plus h squared plus 1 plus h, which is h squared plus 2h plus 1 plus 1 plus h, which is h squared plus 3h plus 2. That's what I got. Okay, and then plug in 1. So I have 1 squared plus 1, which gives me 2. All right. Now I'm going to substitute that into my function up here, which is going to give me the limit as h goes to 0 of h squared plus 3h plus 2 minus 2 all over h, which becomes the limit as h goes to 0 of h squared plus 3h over h, because the 2's cancel. Again, if something doesn't cancel, there's probably an error, because something always cancels. All right, at least a little bit. And then from there, we can split it into 2 fractions, or you can factor out the h. That's the other way of handling it. And then you can cancel the h, and then you plug it in, and you come up with the limit as h goes to 0 of h plus 3, which is 3. So the slope of the tangent line on the graph of x² plus x, as it gets close to 1, is 3. All right, so let's put in x² plus x. And we're approaching the value of 1. And the slope of the tangent line is 3. So if you're further away, if h is further away, then the slope is steeper. But as it gets closer and closer, the secant line approaches the tangent line, the slope approaches the value of 3. This number gets close to 3, and the limit of it is 3. All right. And that's what we're finding, is the slope of the tangent line. Let's do one with the delta x notation. We haven't done one with the delta x notation. This is what you're more likely to see in a physics class. So when I started calculus, I was in physics. I was a physics major. So for me, this was the more familiar of the functions that I had to work with. This is the one that I typically looked at. Okay, so we're looking at this one. we're getting close to the value of 6, and our function is square root of x minus 2. So we're going to be looking at the limit as delta x goes to 0 of f of 6 plus delta x minus f of 6, all divided by delta x. So that's what we're looking at, is that value right there. Now, this again is like the previous one in that it's more complicated. It has a more complicated formula. And so when you plug in, there's more to do. So when we come over here, we're going to want to figure out what f of 6 plus delta x is going to look like. And delta x, again, don't think of delta x as two things, delta and x. It's one thing, delta x. All right, so it represents one value. Delta x is one thing. It's not two variables. So this is going to give us the square root of, and we're going to substitute 6 plus delta x in place of x minus 2. And then if I drop the parentheses, I can then subtract the 2 from the 6, and that gives me 4 plus delta x. Now, I know there's at least 3 students in this class, if not 5, who right now want to take the square root of 4. Thou shalt not take square roots with addition or subtraction. Don't do it. All right? There is no square root when you have addition or subtraction. If you're not sure whether or not you can do something, try it with small numbers that you know. The square root of 9 is 3. The square root of 4 is 2. That will give me a 5, but that means that square root should have been 25, not 13. So that means I can't do that. It's wrong. Okay? So always try it with small numbers that you understand and see if it works. If it doesn't work, then you can't do it. Okay? And the next part is f of 6, which is the square root of 6 minus 2, which is the square root of 4. The 4 is alone. It's no addition or subtraction. So we are allowed to take the radical, which gives us 2. So plugging in, we get the limit of delta x going to 0 of the square root of 4 plus delta x minus 2 over delta x. Now, the first thing that we would try would be to plug it in, right? And see if we get an answer. But if I plug in delta x is 0, that gives me the square root of 4, which is 2. And then 2 minus 2 is 0 over 0. So if I plug in, I get 0 over 0, which is that indeterminate form, which tells me that that method didn't work. It does have a radical in it. So since it has a radical in it, what would you probably try to do instead? Multiply by the conjugate of the one with the radical. So that would give me 4 plus delta x plus 2 over radical 4 plus delta x plus 2. We'll leave the denominator factored out. And we'll multiply together the numerator. That we multiply the conjugate pair. And so it's going to lift off the radical and give us 4 plus delta x. On the outside, I get a positive 2 times the radical. On the inside, I get a negative 2 times the radical, so they cancel. And then I have negative 2 times 2, which is minus 4. Then I'm going to divide this, and I'm going to leave the denominator in its factored form. Delta x times quantity, radical 4 plus delta x, then plus 2. And notice I got some cancellation, but not the kind of cancellation I'm used to. Usually when this happens, I get something in the numerator and denominator that cancels. Right now I've got a 4 minus 4. But 4 minus 4 will cancel. And when that's gone, what do I have that is the normal thing to get after doing this technique? I've got a factor that cancels between the numerator and the denominator. That delta x was a hidden factor, and it was causing this 0 over 0. So I can cancel the delta x's, and that leaves me with the limit as delta x goes to 0 of 1 divided by the square root of 4 plus delta x plus 2. And now I can plug in again. So I get 1 over the square root of 4 plus 0 plus 2, which is 1 over 2 plus 2, which is 1/4. Right? So the slope of our tangent line on the graph of x minus 2 under the radical as we approach 6 is going to be 2. And I'll put that one in the graph. I'm not sure how it does square root. So let's see if it'll take square root. Looks like it does. Square root of, what was it, x minus 6? Was it x minus 6? I don't even remember anymore. X minus 2, and a is 6. X minus 2, and a is 6. All right. And square root of x minus 2, a is 6. What's wrong? What did I, oh, I'm looking at the right thing. It is 1/4. Okay, so I did it right. Whew, I was getting worried there. I was looking at the 2 going, what? Okay, I should have looked at what I circled. All right, so the slope of the tangent line at 6 on the graph of square root of x minus 2 is 1/4. All right, that's what we're finding. Okay. So let's talk briefly about velocities and rates of change and why we take a look at all these. Remember that the average velocity is given by the change in distance over the change in time. So this is change in distance over change in time. And we typically in physics will use S to represent distance because D is reserved for the derivative, which we haven't gotten to all that notation yet, but we will be. All right, so average velocity is basically the slope of the secant line. All right, which is the same thing we've been working with all day, but we've been taking the limit of the secant line, and the limit of the secant line is the tangent line. And it turns out that instantaneous velocity is the limit of the slope of the secant line. So the instantaneous velocity is our derivative at a particular point. So the instantaneous velocity, we can't use the secant line formula because the change in time is 0 and thou shalt not divide by 0. So instead we take the limit of the average velocity as the time change goes to 0. And that will give us the instantaneous velocity. All right. So V instantaneous is given by this formula right here. And this is the instantaneous velocity. Right? So basically it's the same thing, just in a different arena. Average velocity, slope of the secant line. Instantaneous velocity, limit of the slope of the secant line, slope of the tangent line. So now let's take the same thing and let's find the slope of the tangent line at a particular point 1 second after a rock is dropped. So the rock is dropped from a height of 64 feet. It has no initial velocity. It's dropped from rest. So the formula is S of t is equal to negative 16 t squared plus 64. Negative 16 is half of the rate of change of the acceleration with respect to time squared. And so that's where the 16 is coming from. The 64 is the initial height. That's where it's coming from. There's no middle term because the initial velocity was 0. So if the initial velocity were not 0, we would have a t term and the coefficient of it would be the initial velocity. Note that it is negative here because we're calling up positive and down negative, and the rock is going to fall, right? So the distance is going to be negative as it falls. So we're going to use the formula to find the instantaneous velocity 1 second after it's dropped. So we're trying to find S prime of 1, which is going to be the limit as t approaches 1 second of f of t minus f of 1 over t minus 1. So we're going to put in f of t, which is negative 16t squared plus 64. And then we're going to put in f of 1. And we may want to go over to the side and figure out what is f of 1. It's negative 16 times 1 squared plus 64, which is negative 16 plus 64. I'm getting 48. All right, so we're going to have minus 48, right? All divided by t minus 1. Now, if you try to plug in directly the 1, you're going to get negative 16 plus 64, which is 48, minus 48, which is 0, and 1 minus 1 is 0. So if you plug in, you get that indeterminate 0 over 0 form. So there's a hidden factor somewhere that's causing 0 over 0. So we have to try an algebraic technique to see if we can reveal where it is. So we're going to reduce what we have in the numerator. So we have the limit as t approaches 1 of negative 16t squared plus 16. All over t minus 1. And again, if you try to plug in, you're going to get 0 over 0. What common factor could you factor out of the numerator? I'd go for 16, but not just 16. I'd go for negative 16. I want to reverse the signs so that it becomes t squared minus 1 on the inside of the parentheses, and then I can factor out the t squared minus 1 into t minus 1 t plus 1. And there's that hidden factor that was hiding inside of the formula. It was not revealed at first. So we had to do some algebra in order to get it to show up. Now we can cancel the t minus 1 that was causing the 0 over 0 result, which is indeterminate. The function doesn't exist, but the limit might still exist. And now we have negative 16 t plus 1 over 1. And when we plug in 1, we get negative 16, 1 plus 1, which is 2, which is a negative 32. What does that mean? What is negative 32? Negative 32
The velocity.
What? Yes, it's the velocity. Thank you, Juan. It's feet per second. It's dropping 32 feet every second at that particular instant in time, that one moment in time. That's the rate of change of the velocity. All right, it's falling by that amount. Okay. All right, we have another couple of examples to do. The next one comes out of economics and business, I think. Is it the next one or the one after that? Must be the one after that. All right. So this next one has a graph of 10e to the 0.5x, representing the velocity at a point, and the point is 0, 10. And we want to find the average velocity, slope of the secant line for each point with the x value given in the table, and then use the answers to estimate the value of the instantaneous velocity. Now, why are they not asking us to use the formula to find the instantaneous velocity on this particular function? Why are they not asking us to do that? Well, the problem is the function. We're not going to be able to do algebraic factoring tricks with an exponential. They won't work. All right. We'll need a better technique for that. And that's what we'll use when we learn the derivative on Monday. All right. So we're starting with the definition of the derivative, which is a limit. And then we'll move into derivative rules on Monday, which are much easier and a much faster way of doing it than using the limit definition. So the simple thing to do here, of course, is just to go ahead and evaluate where you're wanting to take the slope of the secant line at f of 0 and then f at another point. So for example, on the first one, we're wanting to calculate f of, I guess, 0 minus f of negative 0.1 over 0 minus negative 0.1. All right. And so you would find the values for that. Now, f of 0 represents 10e to the 0.5 times 0, which is e to the 0, which is 1, which would give us 10. So this would give us a 10 minus 10e to the 0.5 times negative 0.1 divided by 0.1. All right. And I'm just going to write down the numbers for you to save you from having to do all of the algebra and arithmetic yourselves. And then I want you to take a guess at what you think the instantaneous velocity is. And again, we'll find a better formula for exponentials on Monday. 99875. 999. Does anybody see the pattern that's developing? It's adding a 9 each time. All right. So what do we think the slope of the tangent line probably is? Well, the slope of the tangent line is probably 5, right? It's approaching 5. And so we can do the value of the tangent line, find the equation of the tangent line at the point. Our point is 0, 10. So we have the point 0, 10. And we have our estimated slope of the tangent line equal to 5. So we do y minus y1 equals slope of the tangent line, x minus x1, which gives us y minus 10 equal 5 times x minus 0, which is y equal 5x plus 10. All right, and that's the equation. And you can see the equation of the exponential by itself here. And here is the exponential with the tangent line put on it. And you can see how it's tangent at the point 0, 10 right up here. Okay. So we're still behind. I think I have time to do one more. I'm going to skip the economics one. The economics one is rate of change of profit. As long as the rate of change of profit is positive, then you would keep doing what you're doing because profits are increasing. But the problem is basically the same. And I want to skip to example 11 and finish example 11, which will finish example or section 3.1. We will put the exam off to Thursday. Okay, looking at this example, we have two vehicles starting out traveling side by side along a straight road, and their position functions in the graph are given by f of t and g of t. F of t is the dark blue, and g of t is this orange-red color that we have here. S, the distance is measured in feet, and t is measured in seconds. We want to know which vehicle has traveled farther at 2 seconds. So we come to 2 seconds and we come up and we look to see what their S values are. It looks like on G, the S value is 1, but on F, the S value is 2. S represents distance. So that means F of t has traveled farther at 2 seconds. So F of t has traveled farther. Its Y value is higher than the Y value on the G function. Then it asks, what is the approximate velocity of each vehicle at 3 seconds? At 3 seconds, the approximate velocity of each vehicle is going to have to be found by finding a line. So the approximate velocity, we would have to take and do something like this, where we can get the slope of the tangent line. So this is the 0.32, and this is the 0.20. So then we can find the slope of the tangent line for the S of equals G of t by doing the slope of the tangent line is approximately equal to Y value minus Y value over X value minus X value, which gives me 2, all right, or 2 feet per second. I repeat the process on the F function, but notice the F function is linear. So its slope is a constant value, and the slope looks like it's going through 1, 1, 2, 2, 3, 3, 4, 4. So the slope of that line is just a 1. All right. So again, on this graph, I've got 3, 3, and 2, 2. So if you want to compute its slope, you would have 3 minus 2 over 3 minus 2, which is 1. And this is on F of t. So the approximate velocity of each vehicle is in feet per second. And it looks like G is moving faster. Why? Because its tangent line is steeper at that point. So the tangent line at 3 is steeper on the red one, even though it's traveled less far than the blue one. It's traveling faster. It started out slower and then sped up. So which one's traveling faster at 4 seconds? So at 4 seconds, I'm going to copy my picture again so that I can do another picture of it. All right. At 4 seconds, I need to think about the rate of change of the tangent line. It hasn't changed on F. It's the same linear function 1 over 1. But on G, it's gotten very steep. So it's definitely traveling faster on the G function at 4 seconds. All right. So the G function is traveling faster at 4 seconds. What is true about the position of the vehicles at t equal 4 seconds? Well, that's where they cross, right? They both touch at 4, 4. And that means that they're in the same location at that point in time. But the G of t, the red car, is traveling much faster than F of t, the blue car. All right. So that's one way of interpreting what it means to be traveling when you're looking at a graph that represents their distance with respect to time. Now, keep in mind, this is not the path that the cars are traveling. The cars are going on a flat road. And this just represents the distance with respect to time.